I'm really happy to see here so wonderful people, so wonderful professors. I'm not so happy to see so small amount of students and people from our university coming to hear these talks. But yes, I'd like to start with the talk of Redner, who will speak about statistics of basketball scoring and league.
Okay. Thank you. Well, it's nice to be here. It was certainly an experience to take the suburban train. That was fun. Can everybody see this? I mean, is...
I can see, but I don't know what.
Okay, good. All right. So what I'd like to talk to you today is a very simple story about basketball scoring statistics. This is work in collaboration with my PhD student, former PhD student Alan Gable, Marina Kogan, who's a PhD student of Aaron Clausette at the University of Colorado. Now, I can't care less about basketball. I can't even watch it on TV. It is the most, to my mind, it is the most boring thing under the sun. But basketball statistics are interesting to me, as they should be for anybody who's interested in discrete mathematics and random walks. And so the basic question that I want to ask here is that can basketball scoring be described as a random walk? So let's try and see what that might be. So for the average person who looks at a basketball game, this is what you might see. Oh, this is terrible video, but and let me turn up the sound for a second.
A sensational play. Not only the slam, which he just popped it.
So this guy that you can barely see, his name is Julius Erving. Has anybody heard of Julius Erving before? One person. He was known as Dr. J in the 70s and 80s. And the reason he was known as Dr. J is that because he had a PhD in dunkology. And dunkology is what he's doing here, is dunking the basketball, like going up over the rim and smashing the ball from above into the rim. And the other guy here is Michael Cooper, who plays for the LA Lakers. He was known as the best defensive player in all of the NBA. And you see that when Dr. J goes up for the dunk, he tries to contest it, and about halfway through he says, uh-oh, I'm screwed, get me out of here. And he just like covers his head and he hides. So most people, when they see basketball, see this. They see enormously talented, physically gifted people doing amazing plays. They're well trained, they're well coached, they do amazing feats of athletic feats. So that's what the average person sees. However, this is what I see. And again, I guess the sun is setting, so it's hard to see, but this is what I see. Can you see it? I'm flipping a coin. I took a movie of myself flipping a coin over and over again. So when I see basketball, this is what This is what I see. I see just coin flippings happening over and over again. And what I want to try and show you in this talk is to give you a sense that basketball scoring is really nothing more than a repeated coin flipping process. So that's really the main point of this talk.
This is a fair coin.
What? This is a fair coin.
Okay, basketball is it like that as well?
Well, that's a very good question, and I will come to that. So that's a very good point. Is basketball a fair coin or not a fair coin? So let's look at a typical basketball game. So we have data for 8 seasons of the NBA. There's like 30 teams. There's roughly like, I forget, it's 6,000 games. And for every single game, we have a record of every single scoring event. So we start off with the game is 0-0, then at maybe 15 seconds it's 2-0, then maybe at 18 seconds it's 3-2, and at 27 seconds it's 5-2. We have that record, and that's the record we're going to analyze. And just to give you a feel for the data, here is a typical time trace of a basketball game. So on the x-axis is the time in seconds. A game lasts 48 minutes or 2,880 seconds. On the y-axis is the score difference. So the score starts out 0-0. And in this particular game, Denver versus Chicago in 2010, Denver raced out to a huge lead, almost 20 points, very early in the game. And for a long period of time, Denver has a very big lead. And then somewhere in the third quarter, Chicago mounts a furious comeback. And then they win, they're leading for a short time. And then at the very end of the game, there's a bunch of lead changes, but finally, Denver wins by 1 point. And so this is a typical time trace, but now we have like thousands of these time traces for all these games, like tens of thousands of time traces. We want to ask, is this time trace a random walk or not? So this is the kind of data that we have. So let's now look a little bit more in detail at what we're seeing here and try and quantify what we're seeing. So the first most simple thing that you can look at is what is the scoring rate? What is the time between scoring events? And the inverse of the time is the rate at which scores occurs. And here is the scoring rate as a function of position, time in the game. And you see that there's something weird happening at the very beginning of each quarter and at the end of each quarter. But roughly speaking, very roughly speaking, we have a more or less constant scoring rate. And this scoring rate is about 0.3, which means that there is a score roughly once every 30 seconds. And that sort of accords with what happens in NBA basketball. There's a 24-second clock. You must take a shot that hits the rim of the basket within 24 seconds or you lose possession. So there's a very strong incentive to shoot a basket within 30 seconds, and that sort of gives us a characteristic time scale associated with the scoring rate. So that's observation number one, a more or less constant scoring rate. And again, you might want to ask, well, what happens over here? What happens over here? I will come to this. Next point is that now that we have an average scoring rate, we want to ask, are the scoring events a random process or are they somehow correlated? And so the way that we try and test for this is by looking at the time between successive scoring events. And so what I'm plotting here is the probability distribution of a scoring interval delta t. And in this plot, I don't pay attention to which team has scored. I just say that every time a score occurs, there's a time delta t, and I'm looking at the probability distribution of this delta t. And one sees that if one plots this on a semi-logarithmic scale, so logarithm of this probability versus time, it's a straight line, which means that this distribution of time intervals is roughly an exponential. So it seems to suggest like a Poisson process, which is describing the scoring statistics. Now, unfortunately, you can't see, there's a few data points. There's a data point here. There's a bunch of data points for very short time, because once a scoring event occurs, like you can't score like an infinitesimal time later. It takes some time to push the basketball all the way down to the court. So there is lesser probability of scoring like immediately after a basketball has been scored. But at least once you get beyond 30 seconds, then you see that it's fitting a very nice Poisson. So that's another clue that the distribution of times between that the scoring events are a random process because the distribution of time seems to be Poissonian. One could ask, well, what if instead of looking at the time between either team scoring, I just focus attention on a single team and ask, what is the distribution of times between scoring events of a single team? And this is what it looks like. And you see that it's essentially the same plot as the other one, except that the time scale is increased by a factor of 2. So it's again showing that the scoring events are seemingly described by Poisson process. One thing which is just amusing is that this distribution actually goes out to 685 seconds. So it turns out that in all the data that we had, there was one game in which it took more than 685 seconds, so more than 6 minutes before a team scored. So sometimes teams can go very cold. And if you watch sports and you listen to sports announcers, they always talk about streakiness and the team is hot, the team is cold. Oh, the team is really cold, they should do something different. But in fact, even in a Poisson process, one can get, with a very small probability, really long streaks where one does not score at all. So it's very easy, if you're looking at Poisson data, to try and see correlations that don't exist. And in fact, this is a well-known phenomenon.
A naive question, if you just restate this figure by, say, time by
Yes, they lie exactly on top of each other. Yeah. So anyways, we seem then, the point is that the probability distribution of time intervals is scaling like exponential in time. Another thing that one can look at is, can we look a little bit more carefully at correlations? And in fact, there's a very beautiful paper that was written in 1985 by this group of people, and they were trying to test for, is there a hot hand in basketball? And so in 1985, with their technology, what they did is they just recorded by hand various players. They'd focus on a single player and they'd ask, what is the probability that a player scores a basket? And was there any correlation in the scoring events? And so using by hand technology, they argued that there was no such thing as a hot hand. And again, if you watch basketball, and I don't know how many of you do watch basketball, but when you watch it, the announcers will say, oh, he's really hot, he should get the ball because he's really hot, or they shouldn't feed him the ball because he's really cold. And this is all like crap, because in fact, there is no such thing as a hot hand. And the way that we measure it is by looking at the correlation function between successive time intervals. So let me call T sub k, we have a bunch of scoring events. Let's call the time between a scoring event, we'll call it t, and for the kth scoring event, let's call it t sub k. And we're looking at the correlation function between t sub k and t sub n, where they're separated intervals. And so if there was any correlation, if I was really hot, then there'd be a short time between a time interval here would correspond to a short time interval down the road if I was like a good player and I was really hot. Or vice versa if I was doing really poorly. So one ought to expect, if there was any correlation, that this correlation function, which I've defined here, would decay as a function of the separation between the scoring intervals. And in fact, one sees that this correlation function is defined to be 1 at n equals 0. You're perfectly self-correlated. But then immediately it's basically negligible. So the main point here is that there is no such thing as correlation between scoring events. There is no hot hand. So this is another piece of evidence that this process is purely a random process. No correlations between scoring events. Okay. So now we've seen that scoring events seem to occur randomly, so it seems like it's a random walk-like process. So the next thing one can look at is what is the mean square displacement of the score difference. So we start off with the game at 0, 0, and this mean square displacement should grow as time. And if it's a random walk process, it should grow linearly with time. And so now I'm plotting averaged over all of our data, this mean square displacement, or this mean square score difference as a function of time. And you see that just looks like a fairly nice linear fit. So this is another piece of evidence that the scoring event, that scoring statistics are described as a random walk process. Someone might say, well, what about over here? I'll come to that at the end of the talk. Okay, so I've now presented to you some reasonably qualitative, some reasonably quantitative evidence that basketball scoring is described by a random walk process because events happen randomly in time and there's no correlation between scoring events and the mean square displacement is growing linearly with time. Now, if it's really a random walk process, then random walk theory tells us very deep things about various observables. And one natural observable is statistics of lead changes. And if we're watching a basketball game, if it's a blowout, we might just be bored and not look at it. But if it's a close game, we're motivated to keep watching the basketball game. And so it makes a lot of sense to focus on statistics of lead changes because these are the most exciting points of the game. And so in the next few minutes, I'm going to talk about how many lead changes occur in a basketball game, how long does a single team lead, when does the last lead change, and if you're interested in real-time game betting, when is the lead safe? And so this is, if you really want to make money off of this, I'm going to tell you how you make money off of this. So first of all, let's ask for the number of lead changes. So again, let's look at a typical sort of an example trace of the score difference as a function of time. So one team is leading, then it's tied, then it's tied, then it's tied. So wherever it's tied, these points are a lead change. And we might want to know, like, how many lead changes occur in a typical basketball game. So before we do that, let's just talk about a pure random walk process. Suppose that we have a random walk process with n steps. And then we know that for evenly matched teams, this is a classic result from random walk theory, that the number of lead changes scales as the square root of n, the number of events. Now, in a typical basketball game, at least in the NBA, a typical score is like 100 to 100, which means, roughly speaking, that there are 100 scoring events over the course of the game. And so capital N is of the order of 100, which would mean of the order of 10 lead changes. So that's what we might expect in a typical basketball game. And so, first of all, we can ask, like, how do we derive this? So let me show you quickly how to derive it. If we have a Gaussian probability distribution, the probability of remaining of having a lead change is just related to the probability of being at x equals 0. And what I have to do is basically integrate this quantity from time equals 0 up to the end of the game. And so I have to integrate essentially 1 over square root of t, or 1 over square root of n dn, and that gives me something that scales like square root of n. So this is where this result comes from. But in fact, there's one important feature of basketball. I'm now going to start introducing some of the idiosyncrasies of basketball, and one of them is this feature of anti-persistence. Namely, when you score a basket, the other team gets the ball. And because of that feature, it turns out if you average over all basketball games, if team A scores, then it scores next with probability roughly 1/3. The other team scores with the probability 2/3. So it means that if I take a step to the right, then with 2/3 probability, I'm going to make a step to the left. And so effectively, there's a restoring force that is bringing you back to the origin that's going to affect the number of lead changes. So it turns out, and here I'm not going to do a derivation, but I think it's sort of like makes a lot of sense, that the relevant probability, the relevant parameter is the ratio of this probability to this probability. And when you have evenly matched teams with this anti-persistence parameter p, the number of lead changes increases by this factor, 1 minus p over p square root. In fact, one can do a lot better than that, again, from classic random walk theory. So I'm not deriving this, I'm just telling you now. If you have a pure random walk of n steps, the distribution of the number of lead changes is also Gaussian. And if I was giving a 2-hour lecture, I would derive this, but I'm not. So I'm just going to tell you this is the result. And so with anti-persistence, all you have to do is just change the effective diffusion coefficient by this factor p over 1 minus p. And so one gets this Gaussian form. And if one compares it to NBA basketball data, it's a pretty good fit to the data. So the red triangles are NBA basketball game data. So overall, like, the thousands of games that we have, the number of lead changes for each game, and the probability distribution. And here is the Gaussian approximation with this anti-persistence correction. And you see that it fits the data reasonably well. It's not perfect, but it's reasonably well. And if one actually does not a random walk, a discrete random walk, but one does, not continuum diffusion, but this anti-persistent Poisson process, then that actually fits the data much better. So it seems that we've at least accounted for some of the major features that describe lead changes. Okay, let me now turn to another very simple, which is how long does one team lead? So here in this game, Denver is leading. It leads all the way almost to the very end of the game. Then Chicago takes a short lead. Then Denver is leading again. Then there's a tiny little interval where Chicago's leading. And then Denver wins at the end of the game. So what we're asking for is the length of this stick. So what is the length of the stick? What is the probability distribution of the length of the stick compared to the length of the entire game? So you might imagine, well, clearly, if the teams are evenly matched, the average length of the stick should be 1/2. It doesn't matter which team is leading. But what I'm asking is a deeper question, which is what is the probability distribution of the length of the stick? And if the teams are evenly matched, clearly this probability distribution should be symmetrical about half the length of the game. So if I ask now, what is the probability distribution of the length of the stick versus the fraction of time leading, what do you expect? Symmetric about 1/2, right? And what about this? Is this a good guess? The teams are equally matched. They're trading baskets all the time. They're trading a lead, fairly often. Shouldn't it naturally be the case that the number of lead changes, or the fraction of time that one team is in the lead, is peaked at around equal probabilities? And if you believe this, good because I've told you exactly the wrong answer. It's exactly the opposite. Here is the data. So here I'm plotting the probability distribution that one team is in a lead as a function of the time in the game. And instead of having a peak at halfway, it's actually a minimum at halfway with peaks at either all 0 or all 1, meaning that one team is leading essentially all the time. And in fact, this is actually a manifestation of a classic result in random walk theory, the arcsine law. And so here is a 0 parameter fit between the arcsine law and the NBA data, and you see it's an incredibly good fit. So amazingly enough, when you accept that random walks that basketball scoring is described by random walk, very deep properties from random walk theory then can be applied to this result, to observables in random walk theory. Anyways, that's called the first arcsine law. Let me show you another one where I can actually derive everything in full detail, which is when does the last lead change occur? So again, we have some trace of the score difference. At some point, the lead changes hands, and after that point, one team is in the lead until the very end of the game. And I want to ask, when is this time, and what is the probability distribution of this time? So let's see. So let me show you how you derive this result, because actually you can derive it by elementary means. And so first point is that in order that this is the last lead change, we must have that my random walk is at the origin at time t. It must return to the origin at time t. And now a very useful perspective to get the rest of the result is to note that for the rest of the trajectory, the random walk always has to stay for x positive. So if I reverse my perspective and say, let me start at some unknown position x, and I must return to 0 exactly at this time t. So if I go backwards in time, we are just actually asking for the probability of a first passage starting at x and ending at the origin at time capital T minus little t. So that's what we have here. Now each of these quantities is well known. The return at time t is just the Gaussian probability evaluated at x equals 0. And the first passage probability is given by this quantity. And if you've not seen this, let me just derive it for you really quickly. This is what we all know for a random walk. Where is it? It's given by the Gaussian probability distribution. But if you want to ask what is the probability that it comes to the origin for the very first time, well, here is the result. Let's imagine that a random walker starts at x naught, and here is time going to the right, and we want it to come to the origin for the very first time at time t. And the way that you can get this result is to essentially say, well, if I want to have only the probability, the random walkers that do never cross x equals 0, you can use the image method from electrostatics and say, well, that probability distribution is just the Gaussian probability plus an image contribution at minus x naught, with a minus sign, and the plus here means that it starts at minus x naught. And these two Gaussian, the Gaussian and the anti-Gaussian will be such that they always give you 0 value at x equals 0. So by the uniqueness theorem, if I have a solution to the diffusion equation, two solutions that satisfy the same boundary conditions of the same solution, so this is the probability distribution in the presence of an absorbing boundary at x equals 0. And now what we need to just do is compute the flux to 0, and so you just do this and you end up with this quantity. So that's how you derive the first passage probability easily. Now, one thing I just want to emphasize about this is that an amazing feature about this, which some of you may or may not know, is that if I integrate this quantity over all time, so that's the probability that I will eventually hit the origin at any time, this probability is equal to 1. We are guaranteed to hit the origin. No matter where we start, as long as we're willing to wait long enough, we will hit the origin. But because of this power law tail in the distribution, the average time to hit the origin is infinite. So this dichotomy, that you're sure to hit the origin, but the time you have to wait to hit the origin is infinitely long, is a source of what makes random walks so alluring, so beautiful, so weird. And so it's worth emphasizing. Okay, coming back to my main problem here, we have our occupation probability, this first passage probability with the time argument capital T minus little t. And so what we want to compute now is the probability that the last lead occurs at time t. So we just have to take the probability of being at the origin times the first passage probability. The only other thing is that the final point of the score difference, we don't know what it is. So we just integrate over all possibilities. And there's a factor 2 because the score difference could have been positive or negative. And this is an elementary integral, and you get our good friend, the arcsine law. This is called the second arcsine law. And even though it's a different phenomenology, it has the same functional form. So second arcsine law. Let's look at the data now. And so here is the NBA basketball scoring data of the probability distribution when the last lead change occurs. And so you see that it looks very arcsine-ish. And let me just compare it with different kinds of hypotheses. So this blue is the result of a homogeneous Poisson process where we simulate, millions of basketball games where we take the average scoring rate of 0.3 and just play it over and over again, keep track of the last lead change in a game, look at the distribution. So that's what the homogeneous Poisson process gives us. One can do actually a lot better because we saw that the scoring rate had little glitches at the end of the first half, the end of the third quarter, the end of the game. And if you actually use the exact scoring event second by second in the game with increased scoring rates at the end of the first, second, third, and last quarters, you actually fit the glitches in the data pretty well. And finally, this was the arcsine law. So you see it fits really well. So let me now try and give you an intuition for why there are 2 peaks, because that is very hard to wrap your head around. But it turns out there's a very simple way of understanding this. So let's imagine here is a typical trace of a random of scoring in a basketball game, and suppose that the game finishes over here. Notice that I've plotted this versus log t. This is a crucial thing to get some intuition. When you have a scale invariant process, it makes sense to try and present things in the right scale invariant way. So I'm plotting it versus log t. And in this particular example, we see that the last lead change happened over here, which is just a little bit before the game was over. So in this particular example, the last lead change occurred very near the end. Now let's look at another trace. Here's another trace. But because this is on a logarithmic scale, this is like, if this is like, say, 10 to the 6th, this is 10 to the 5, that's 1/10 of the way. It's like very much near the beginning of the game. So here the last lead change is very close to the beginning of the game. And the crucial point is that when you plot things in the scale invariant way, that either you'll find that it's very hard to engineer to have a lead change halfway through the game. It's either more likely to occur near the beginning of the game or near the end of the game. So this is a simple mechanism for why there are 2 peaks. Now, you asked the question, what about different team strengths? And in fact, we can do this. So when there's equal team strengths, the probability distribution of the last lead change was this, which is obtained by integrating an occupation probability and a first passage probability. If there is a bias, then the same mathematics goes through line by line. It's a little bit more complicated, so I'm not showing any of the details, but you end up with this functional form. And if you plot it, here is the lead change, the probability of last lead change at time t, and I'm showing it for different biases. So as you increase the bias, it gets more and more skewed. And it turns out that the red is the value that one finds in NBA basketball. If you average over every game and ask, like, what was the average score difference from that, compute an average bias velocity, then you end up with this slightly skewed probability distribution. However, if we really want to do this correctly, what we should do is we should then just average over all biases. We should then look at every single game, find the bias for the game, compute this skewed distribution, then average over all biases. And when you do that, amazingly enough, you get back exactly the arcsine law. So here I'm showing the comparison between the arcsine law and the same data I showed in the previous slide when I average the distribution of team strengths. And in fact, I've even sort of been a bit more general because I've included the possibility that the anti-persistence is stronger. It's stronger than what it really observed and is what it's observed. And you see you can't tell the difference between the data. So this feature of different team strengths actually plays a negligible role in NBA basketball scoring statistics. Next thing I want to mention, and this is for anybody who's interested in gambling. Who cares about gambling? Okay, when is a lead safe? So suppose you have a time trace of a game. You're a time tau left in the game. There's a lead L. What is the probability that that lead stays safe? And again, using this random walk or diffusion picture, we know what the answer is. The probability that this lead is safe is the probability that a random walk that starts a distance L away from the origin does not return within time t. And so this is just related to 1 minus the probability that you do return within time t, which is just the integral up to time tau of the first passage probability. And this is an elementary integral to do, and you get just this very simple error function form. So here is the answer. And it depends not on L and tau separately, but it depends naturally on the scaling combination L over root tau. And to give you a feeling, so here is a plot of this safe lead probability as a function of the scaled lead size. And to give you a feeling for numbers, if you have a 10-point lead with 8 minutes to go in the game, then you end up with 90% chance that the lead is safe. So if your bookie is giving you different odds than 90% with 10 minutes with this type of a lead, you know to start betting. What is the data say? So here is the NBA basketball game data. Here is our theory. And there is a guy in the United States who's very famous, known as Bill James. He invented this whole field of quantitative analysis of baseball. It was called sabermetrics. And so he's infinitely more famous than me. He's infinitely more rich than me. But here is his prediction. Here is the data. And here's our prediction. Okay. So can basketball scoring be described as a random walk? So I argue yes. But there's some buts here. And so let's now spend a few minutes talking about some buts. Because basketball is clearly not just a pure random walk process. But let's try and deal with each of these in turn. So first was the anti-persistence. We saw that when one team scores, it then scores again successively with a probability roughly 1/3. And we've taken care of that. And we've seen that it really plays no role. Another feature which is really bizarre about basketball is that if any of you watch basketball, especially NBA basketball, especially in the playoffs, you know, the game is supposed to be 48 minutes long. The first 45 minutes take about an hour and a half. And if it's a close game, the last 3 minutes can take forever. There's a timeout every few seconds. There's all kinds of weird things going on. So the last 2.5 minutes of an NBA basketball game are completely anomalous. And again, if we just look at the scoring rate, we see that, you know, right here at the end of the game, the scoring rate goes up by roughly a factor of 2. So even though the game seems to slow down, it's almost like relativity. Even though the game is slowing down, the basketball scoring rate is actually increasing by a factor of 2. And here's another feature, which is that this growth of the mean square displacement has this anomaly which happens in the last 2.5 minutes. And how is this manifested? So what we can do then is let's look at the distribution of score difference at various times in the game. So here's the score difference after 1/4 has gone by. And you see that it looks like a nice Gaussian, as you might expect from a random walk picture. And so I'm plotting the probability of a score difference versus a scaled displacement. So it's basically the score difference divided by the square root of the time. And at the end of the first half, it overlaps the data perfectly. At the end of 3/4, it overlaps perfectly. At 45.45 minutes, it overlaps perfectly. But at the end of the game, this happens. So this, is, in fact, I think is quite an amazing feature that NBA basketball, last 2.5 minutes are completely different in character than the first 45 minutes. And I don't know how to characterize this. Okay, so the last 2.5 minutes are anomalous. As you correctly pointed out at the beginning of the talk, teams are typically unevenly matched. And what I would say is that, yes, they're unevenly matched, but not that unevenly matched. And I'll make this more precise in just a moment. And in fact, it doesn't even matter. Their differences are so small that it doesn't matter. And to try and illustrate this, let me say one more thing because it's going to be relevant to trying to discuss this feature of the bias. There's also one more feature about basketball games, which is that if you have a 40-point lead and there's 20 minutes left in the game, what do? You send in your subs, you sit on the bench, you make jokes, you're very relaxed. But if you're 40 points behind, you start getting very desperate and slinging a lot of 3-point shots and trying to do desperate things to try and catch up. And in fact, if you look at the scoring rate as a function of the lead size, there's a systematic trend that if you're way behind, your scoring rate is a factor of 50% more than if you're way ahead. So there is this reasonably nice systematic feature. So using all of these observations, I want to show you how you can build a computational model that describes many features of basketball games. And this computational model is based on a very simple model for competition, a classic model by Bradley and Terry in 1952. And the idea is the following. Let's imagine we want to understand the statistics of winning and losing in some kind of a sports league where each team has a strength X. So X alpha is the strength of team alpha. So given the strengths of each team, we want to calculate what is the probability that a team alpha scores in a typical basketball scoring event. And the Bradley-Terry model says this, that the probability that team A scores is the strength of team A divided by the sum of the strengths. It's just the simplest possible model you can imagine. And so in this kind of a model, the absolute team strength doesn't matter. It's just relative team strength. So one can always normalize so that the average team strength is 1. Now, this is not quite complete because we've seen, because of the anti-persistence, if I've just scored, there's a smaller probability I'll score again. If I was scored upon, there's a higher probability that I was scored upon. So I've got to put in these corrections for anti-persistence. And then there's a second correction because of the fact that if a team is way ahead, it doesn't score as quickly. When a team is behind, it scores more rapidly. So we put in these two empirically observed phenomena. And now we can make a computational model. We have these probabilities. We play millions of seasons of basketball games, and we can then measure all kinds of basic quantities. And the only input, or the only variable in the model, is what is the probability distribution of team strengths. And so without any prior knowledge, it's natural to try a Gaussian probability. And as we've seen, the mean can be 1 without any loss of generality. And so the only variable, we have a one variable problem, which is the variance in the team strengths. And so if we do that, then we can, as I say, play millions of seasons of basketball. We can measure everything we want. And so I'm showing you like some typical things that we measure. What is the winning fraction versus rank? What is the time one team is leading in the game? The number of lead changes, the score difference. And so what I'm plotting here is as a function of this single parameter in the model, which is the variance in the strength of the teams, I'm plotting I'm plotting like the, so like for example, the time that one team is in the lead. So there is some probability distribution. There's some quantity, the time that's in the lead. And what I'm plotting is chi-squared versus the minimum chi-squared. So that is that when I vary this one parameter, this time that one team is in the lead has this quadratic dependence, and somewhere, for some value of the strength, it reaches a minimum. And for all these different other variables, you see there's a minimum almost at the same point. And if one integrates all of these different quantities and computes like either the geometric average or the sum of these things, one finds that there is a global optimum when sigma squared is 0.0083. So when I choose my only one parameter, there's only one parameter in the model, I choose it to be this way, I minimize the deviation of what I observe in simulations with real NBA basketball scoring data. So the upshot of all of this is that we find this mean square variance of 0.0083, which means that 2/3 of all team strengths are within 1 plus or minus the square root of this quantity, which is basically 9%. So it shows that in NBA basketball, the strongest team has a relative strength of 1.09. The weakest team has a strength of 0.91. They're actually very evenly matched, and we were actually able to quantify this. So the point about this last feature, that the team strengths are very closely matched, is that if you think about NBA basketball, these are teams made up of people who've gone through many levels of filtration. They were the best player on the high school team. They were recruited to college. They were best player in college. They were drafted number 1 in the NBA. They are like incredibly well-trained, well-coached, well-strategized athletes. And the point is that when you're dealing with this kind of evolutionary process where people are always trying to figure out what is the advantage to get better than somebody else, all you're doing is you're just getting rid of any systematic effects, because if I have an advantage, someone else figures it out and figures out a strategy to counteract it. So all that's left is random walk fluctuations. And in this particular case of NBA basketball, the team strengths are so close to each other, really all you see is random walk fluctuations. So my final slide is just this. Can basketball scoring be described as a random walk? With a naive random walk picture, I said yes. I've now shown you a somewhat more sophisticated, data-driven picture in which we actually correct for some of the small features that are idiosyncratic to basketball, and the answer is still yes. I'm done. Thanks for your attention.
Okay, questions or comments?
I think that there's also one more thing which you can test. If you know what is the probability that the team which scored will score again, actually is less than 1, then you should have just a statistics of the length of points scored by one team in a row. I mean,
yes, but we have that. That was this, that was back here. Let me just go back to it. Oh, it's raining at 40 degrees in Santa Fe. This plot here. So this is the time between scoring events. This was for a single team. This is for either team. But you see they're fitting by Poisson. And then the other issue is the fact that there seems to be no correlation between the scoring events.
That you should not know what is the maximum, what is the length of the maximal, numbers of points scored.
Well, actually, what we looked at in this previous plot, we took data for, here, where is like the last data point here? And for a single team scoring, there was 685 seconds where one team, some poor team that was just playing really crummy, did not score an event. We did not look at the other side, which is the minimal scoring events, but the problem is that with minimal scoring events, they're very artificial because, you can do this thing where you call a timeout and you can take the ball halfway up the court. So you will see anomalies for very small scoring intervals, but I'm not sure how real it is and how much is artificiality of the rules. So my first question is, have you ever seen a basketball game? No. Okay, so that's the reason you're asking the question. So the point is that when a team scores a basket, the game does not start like at the center. What happens is the other team gets possession of the basketball, and because they have possession, that gives them a big advantage, and that's why they score with a higher probability. So it's different than soccer. Have you seen soccer or football? Have you seen any sports game? Badminton. Okay. Well, anyways, there are many sports, like in soccer, when the team scores, the ball is returned to the center of the field, and then the teams compete for the ball, and it's like the next event is uncorrelated with the previous event. But in basketball, the other team gets the ball, and so it gives them an advantage, and that's why there's this 0.35, 0.65.
And that value was just empirical?
Yes, that's what that's what the data says.
And so what about other sports?
Well, okay, good question. So first of all, we did look at other sports, and we looked at NFL football, NHL hockey, college football. We looked at as many sports as we could find. The problem with a lot of these other sports is that the scoring rate is very small. So in hockey, we could probably assemble a similar data if we could wait 1 million years and get 1 million years worth of data. Other sports, they have like idiosyncratic rules. Like in American football, there's a touchdown which is worth 7 points and a field goal which is worth 3 points. So it's not as clean, but nevertheless, similar features you can see in these other sports. It's just that the cleanest signal is in basketball. What?
What's your favorite American game?
What is my favorite?
No, I mean the baseball.
Oh, what about baseball? Well, I mean, baseball is a very, first of all, baseball is a very strange game, as you must appreciate. It's bizarre, and it's not played, well, it's played in Japan, I guess, pretty avidly. But, in baseball, it's not a flowing game. You have these innings, they're divided. So, you know, somehow in baseball, looking at the game statistics wasn't, or scoring statistics didn't seem to be very meaningful. We just didn't know how to do it. What we did look, though, at was things like team scoring streaks and team batting streaks. And there's all kinds of beautiful data to be mined there. And I could give a whole new other talk about baseball scoring statistics, but it's another talk.
Okay, if no more questions, let us tell you once again.